at some point, if someone can type into the chat box, say hello, I'll know that it's good. Oh, great. Thank you very much. Good. Very good. Um, what I'd like to do is, since we have a test coming up for many of us, I'd like to go through some basic steps. I'm going to concentrate today, and I'm going to maybe try and do another session or either record something and just post it tomorrow. I'd like to go through some steps that might help us go through these problems. We're going to start with confidence intervals, then I'm going to move on to hypothesis testing, the t-tests. Okay, so let's kind of outline some things that we know we need to do in order to get solve problems that we have. Okay, so I'm going to start with confidence intervals. Okay, so when working with confidence intervals, you might be asked to determine what the confidence interval is for some point estimate. Okay, point estimate could be a mean or it could be a proportion, right? So number one, what's the point estimate? Okay, is it X bar or is it P cap? In other words, we want to, are we working with a sample, numeric sample, or are we working with a categorical sample or proportion? Of course, we're looking for the confidence interval for the true mean or the true proportion for that population, working with having known what the mean is and what the proportion of our sample is. Okay, so in either case, we're going to start with determining, well, which of these two are we working with? One of the reasons we want to know that is because we're going to eventually have to calculate the standard error. It's going to be a slightly different way to calculate it in each case. Okay, so that's number one. So let's say I have a problem. And the problem is that I have a sample of 36 people. Sample size is 36. I have 36 people. The average weight for those 36 people, okay, is equal to 150 pounds. And the standard deviation, right? Now I'm gonna put this two ways. Standard deviation or sigma, standard deviation of the sample or standard deviation of the population is equal to, let's call it 10. Say I want to calculate a confidence interval now. So the first thing I want to look at is, well, what kind of point estimate am I looking for? Well, this is a numeric mean that I'm looking for now. That's the point estimate. I'm using X. I have X bar. I'm looking for the confidence interval for the mean. Okay, so first thing I might want to do is, okay, so the mean is 150. So I know the formula that I'm going to use is X bar plus or minus some margin of error. And that margin of error is equal to either a value for Z or a value for T. Okay, so that could either be Z or T that I'm going to put in here. When we're using T, we call it T critical. Okay, because it's the value of T for that number of that sample size, that number of degrees of freedom, and so on and so forth. Okay, so, well, which of this am I working with here? I haven't identified it yet, have I? Right? So if I say that you know the standard deviation for the population, we would use Z here. Okay? Now Z, if I'm looking at a 95% confidence interval, we know because of the way the normal distribution is and our sample means would be distributed in the central limit theorem, we know that 95% confidence interval represents a z-score of 1.96. If we work with a 99% confidence interval, it would be 2.58. And if we, in other words, have to be further out in order to have 99% confidence that 99% of the time we would not get that extreme of value for t if our sample mean in capturing our various sample means. Okay, and for a 90% confidence interval, we would use 1.64. Okay, so if I know the standard deviation, that's what I'd be after, right? So if I know the population standard deviation. So number one, what's the point estimate? In this case, it's X bar. Number two, what's the confidence interval that I'm working with? Number three, do I know sigma? Right? Well, okay, let's see. In this case, I'm going to say that I know sigma, right? And I'm going to say the confidence interval we're interested in is 95%. Okay, so I've gotten through 1, 2, and 3. So if I know sigma and the confidence interval is 95%, I'm going to use, for z, I'm going to use 1.96. So I'm down to x bar plus or minus 1.96 times my standard error. Now, how do I calculate my standard error? My standard error is equal to sigma, the population standard deviation, over the square root of the sample size. If I don't know this, it would have been the standard deviation of the sample over the square root of the sample size. So it really doesn't change that much as far as our calculation is concerned. So in our case, it's 10 over the square root of 36, which is 6. So it's 10 over 6, which is 1.667. Okay, remember, I don't want to round until I get to the very end of our calculation. So I'm going to be a little bit more rigorous than I usually am, just to keep simulate what you might have to do on the homework or on the test in order to get the right answer by the time you get done. Okay, so that's what our standard error is equal to in this case. So I calculate my standard error, that's for number 4. Calculate my standard error, right, using the correct formula, right, depending on whether it's S or sigma that I know. Right, now, number 5, I calculate my margin of error. And what is my margin of error? My margin of error is 1.96 times our standard error, which is 1.667 in this case. So let's see. So if I calculate our margin of error, I'm going to take out my calculator and do that. Well, x bar is 150 plus or minus. Let's look up what the value of that's going to be. Okay, and I'm going to say 1.96 times 1.667, and that's equal to 3.2, roughly 3.27. Okay, I'm going to save that number in memory. Oops, let me recall that so I can write it down. 3.27. 3.27. You're going to notice that when I go back to the calculator, I'm going to use the actual number, not the rounded number now. Okay, so now I'm going to add and subtract my margin of error. 6. Okay, and number 6, I'm going to calculate my confidence interval by adding and subtracting the margin of error. Okay, so go back here and calculate it. So it's going to be, let's see, it's going to be, clear, memory's still there. So it's going to be 150 minus my margin of error. It's going to be equal to 146.73. Comma, and I'm going to go back and calculate the addition. Clear. Okay, I'm going to put 150 plus my margin of error. It's going to be 153.27. Okay, and there I have my 95% confidence interval. Okay, so now what if I change something here? Let's take a look at this. Look at the same 6 steps, except I'm going to change one thing. This time I'm going to say I don't know my standard deviation. The standard deviation I'm working with came from my sample, right? My sample of size 36. Okay, now I kind of made it a little bit kind of weird here. I'm going to stick with the 36 for the time being, right? But we're going to talk about sample size in a moment, okay? When you don't know the population standard deviation, if that's not known to you, the only way that you know the variability in the population is by using the variability in the sample to estimate it. In other words, the standard deviation of the sample. Let's say it comes out to 10. Okay, so now in this case, I don't know sigma. So we're dealing with the same point estimate, a mean, right? We're dealing with a confidence interval. I'm going to say 95%, and we're not going to change that. This time, I don't know sigma. So instead of using the z-score 1.96 for a 95% confidence interval, I have to use the t-score instead to calculate my margin of error. So what is my t-score going to be for this particular problem? Well, it's going to be based on my sample size, right? My degrees of freedom. Okay, so let's look up the T. By the way, there's a t-table in the book also that you could use if you prefer that. So I'm going to pull up a t-table, any t-table, in this case, the one we've been using in class recently. And I'm going to go for the sample size is 36, so the degrees of freedom is 35. Well, there is no 35 here because we're getting on to the upper part of this table, right? But I can go across, and our 95% confidence interval is in the middle, right? Here, if I wanted 99% confidence, alpha is equal to 1%, I'd use this column. If I wanted a 90% confidence interval, I'd use this column. Notice if it's a super very large sample, then what happens is that you get 1.96, 1.64, and 2.58 for our confidence intervals, just as you would get if you were using the z-score. Well, simply because you're testing the whole population, right? Infinity means you're basically testing the whole population. So let's look at 30 and 40. It looks like our critical value of t, the distance apart that our values have to be in order to be capture 95% of the samples if we knew the actual population mean, or in other words, to be 95% certain that I've captured the population mean between those two numbers, would have to be, let's see, that t-score would have to be either 2.04 or 2.02. Well, what I might do is since the value I'm looking at, the degrees of freedom is 35, I'm going to use a value in between. I'm going to call it 2.03. Okay, for my critical value of t, right? Usually it's a smaller sample size. You can just read it off of here because they're integers up to that point, right? So I'm going to use 2.03 for our value. So I need to use that instead of t because it makes up for the uncertainty that I have by not knowing the population standard deviation. So this becomes 2.03. Okay, let me try and make that a little bit darker. 2.03. So we know our confidence interval. We know sigma. We don't know sigma. We know we're going to have to use the standard deviation. So we don't know that. So we accommodated for that by using the t-score. Now I'm going to calculate the standard error. Well, the standard error is calculated the same way, except we use the standard deviation, which is 10 over the square root of 36. That hasn't changed. So our margin of error now, because we're using we're using t instead of z, our margin of error is going to be larger because I'm multiplying by 1 point. Adding and subtracting a bigger number when I'm multiplying and when I add and subtract the margin of error. Okay, so you might want to consider that. One of the questions on the test might be, well, if you use t-score or the z-score, is the t-score margin of error going to be wider or narrower than a z-score calculation, or when you know the population standard deviation? So you kind of can deduce what that answer might be. So in this case, let's go back here. Clear the memory also, because I have to calculate the standard error again. Our margin of error, rather, 2.03 times 1.667. Okay, so our margin of error now is 3.384. So I'm going to put that into memory. I'm going to clear this. 150 minus our margin of error is equal to 146.6. 146.6, I think it was 61, comma, and adding to it, I probably don't need that, I guess, right? It's going to be 153 point, let's see, 153 point, where did I calculate my margin of error here? Oh, I didn't write it down, so I have to go back here. 150 minus, excuse me, clear, plus memory, it's 153.38. So we can see it's a wider range than the range that we had when we knew the z-score. Okay, so that kind of covers it. Number one, what kind of point estimate are we dealing with? Mean or proportion? Do we know the confidence interval that we want? We have to know that in order to calculate it. In this case, it was 1.9. That was 95%, right? So if we were 99, if we were going to use a z-score, we used 2.58. If we were 99%, and we didn't know the standard deviation, then we would have to go to the table and use the column for 99% and the degrees of freedom for it based on our sample size. Okay, and maybe I should add that in here, right? That should be in here. Let's see. Do we know sigma? Number 4, our sample size, right? Okay, and calculate our standard error, which we did. Then calculate the margin of error, which is our t-score or z-score times our standard error, and then calculate confidence interval by adding and subtracting the margin of error from the point estimate, from x bar or p-cap, if that's what it happens to be. Let's do that again, except this time, let's do it for p-cap. Let me see if I can't do this. Okay, number 1, let me copy all these, number 1, number 2, number 3. Okay, 1, point estimate. Okay, what is it? 2, forgot it already. What confidence interval we want, what sigma, what's n. Confidence interval, 3, sigma, or S. 4, what's our sample size? 5, calculate our standard error. 6, calculate our margin of error. And 7, calculate our confidence interval. Okay, so let's say I have a situation where I survey I survey 500 people on Coke is coming out with a new flavor. I survey 500 people, and I want to know what percentage of these people, of the population of the United States, would prefer the new Coke. Now, you guys are too young to remember this, but Coke tried this a long time ago, and it was a disaster, right? New Coke flavor, new Coke formula, actually. New Coke formula, right? Okay, and I want to know whether the country's going to like this. I'm not really interested in just these 500 people, but I'm interested in whether the rest of the country and China and Russia and wherever the hell else they sell Coke, how they're going to react to this. So I'm going to randomly sample 500 people. I'm going to ask them to take the old Coke and the new Coke, and I'm going to ask them, did you prefer the new Coke? Let's say that 300 people preferred, out of the 500, preferred the new Coke. Well, our proportion of the sample that preferred the new Coke, in other words, our p-cap, is equal to 300 out of 500, right? Or 60% preferred the new Coke. Okay, so that sounds pretty good. Now, well, what do I really know about P, the total population proportion? Well, 0.6 might be a pretty good estimate, but I really don't know. I need to calculate a confidence interval to understand how certain I am about that number. Okay, so first thing I'm going to do is, what is the point estimate here? Well, in this case, it's a proportion. It's not a mean, not a numerical variable. Okay, the confidence interval. You know, this is really important. going to spend a lot of money on advertising. We're going to lose a fortune. The board of directors will fire me. You name it. So I want to know with 95% certainty. I want a 99% certainty. I want a 99% confidence interval. Now, do I know sigma or the standard deviation? And why do I want to know that? Because I want to know whether I should use T or Z. Well, normally, all I know about this sample is what I know from the sample that I took. So I really don't know that per se, but you want to know something. When we're dealing with proportions, our rules say we have to have a large sample size, right? Say 100 or more, for instance. Okay, and not only 100 or more, but we should have 15 at least in each group. People that liked it, people that didn't like it. We have well over that. We have 300 and 200. We have a total of 500. So well over that. So for proportions, we're going to allow ourselves to not use the t-test because of the sample size, and we're going to use the z-score instead. When I get done with this, I'll come back to the question of sample size on the previous problem. Okay, so we're going to use the z-score instead. So our sample size is 500. Okay, always going to be big, so we're not going to worry about that. Now I have to calculate my standard error. So let's write out a formula here for our confidence interval. P cap plus or minus, I'm going to use z. So z for 99% is 2.58 times my standard error. Okay, how do I calculate my standard error for proportions? Well, it's equal to the square root of p times 1 minus p over the sample size. Okay, in our case, that's going to be equal to, since we only know p cap, we'll use that. It's going to be equal to 0.6 times 0.4 over 500. Okay, so our standard error is equal to, and I'll pull out my calculator to do that, 0.6 times 0.4 is that divided by 500 is this, and I'm going to take the square root of that. Okay, so it's 0.022. I'm going to call it 0.022. 0.022. Okay, is going to be our standard error. So I'm going to go back to my formula. P cap was our 60%. That's our estimate, point estimate. 0.6 plus or minus 2.58 times 0.022. Okay, remember that was because 99% confidence interval. So I've calculated my standard error. Now I have to calculate my margin of error. So let's calculate our margin of error. And again, when I go back here, since I'm using a calculator with that's memory, I can clear memory and I can store this number in memory. And then I can clear my register here, my display. Then I can say, okay, let's go ahead and calculate that. Let's see, it was 0.6 minus, but did I calculate my confidence? I guess I didn't. Hang on a second. Let me see what I have here. That's 0.021. Oh, I didn't multiply it out yet. Okay, times 2.58 is equal to 0.5. In other words, our margin of error is 2.58 times that number we calculated for our standard error, which was 0.022. I got ahead of myself a little there. I'm going to clear out this memory again, and I'm going to put this number, which is our margin of error, into my memory. Okay, I think I did click it there. So now I can go down here and I can calculate my confidence interval. So my confidence interval is going to be my point estimate, 0.6 minus our margin of error, which was 2.58 times our standard error, 0.022. I'm going to recall that, equals 0.543. 0.543. Okay, and let's take a look at an upper limit for a confidence interval. Okay, I'm going to clear the display. Still got that margin of error in my memory, and it's 0.6 plus our margin of error is going to be 0.6. I'm going to 0.657. 657. It looks like. 0.657. So I am 99% certain that if this was truly an independent sample and truly a random sample of people, say in the United States, I'm 99% certain that the true population proportion of the United States that will prefer the new Coke formula is between 54.3% and 65.7%, right? So I'm 95% certain that more people than not, in other words, over 50%, would prefer this new Coke formula. Well, unfortunately, when they did this in like 1975 or 1970, they got it wrong. So they actually had to go back and they started selling something called Classic Coke because everybody wanted the old Coke. So at any rate, but that's neither here nor there. Now, just one extra thing I want to bring up. If I go back to this problem, notice I said if we knew the standard deviation of the population sigma, that we would use the z-score here. If we didn't know the population of the standard deviation of the population, we would then calculate a t-score based on the sample size and on the which tells us the degrees of freedom, right? 1 minus the sample size. Okay, so if you do that, you'll never be wrong. You'll never make the wrong choice. However, it's not uncommon because of the way that the t-distribution works and how the sample size impacts on it, that as you get to a very large sample size, you get closer and closer to what the z-score would be. For instance, sample size of 100 is a z-score of 1.98. Okay, so in other words, your margin of error when you calculate it would only be off by, say, 1% or so if you were to use 1.96 instead of 1.98, right? So, in other words, 0.02 out of 2, right? That's only like 1% or something like that. Now, if you can tolerate that much error, when you get to a large sample size, you might consider saying, sample size here is 100. So even though I don't know sigma, I'm just going to not waste it. I'm not going to spend a lot of time looking up what the t-score is. I'm going to call it 1.96 and just go ahead and do my calculation. Hard to argue with that logic, especially if maybe you're doing a first pass at the data. It's not going to be what you publish and so on and so forth, and you want a quick look at it. So you could certainly do that. Now, it's arbitrary what you call a large sample. Some textbooks say anything over 30 is a large sample. Some textbooks say anything over 100 is a large sample. Put it this way, you're never wrong if you use the t-score, right? But if you have a very large sample, like over 100, it's not outrageous to use the z-score instead. Okay, so say 1.98 or something like that. So you can go ahead and do that, but keep in mind that the right way to do it is to use the t-score and using the z-score for a large sample is kind of a shortcut. But in most cases, if it's really a big sample, it'll work. Okay, I just want to take a quick look. I don't see any questions so far, so I'm hoping this kind of clarifies this for all of us a bit, right? That's the steps that we would go through in order to calculate a confidence interval. So how do you guys feel about that? Okay, good. I'll try and write that out so that you can actually go 1, 2, 3, 4, 5, go through all of these steps yourself. Okay, so now let's do the same thing with hypothesis testing. Okay, so when we do hypothesis testing, right, what are we doing? Well, in that case, we are, like in a study, if we're doing a study, we are going to take two groups and compare them, right? So I want to know, well, let's see. I'm going to take the same thing I talked about before, well, maybe a little bit differently. Let's see. How can what numerical variable can I substitute here? I'm going to say, okay, I'm going to take doctors and lawyers. Okay, and I want to determine who makes more money. Does doctors make more money or do lawyers make more money? So I'm going to look and I'm going to, now keep in mind a lot of these are word problems, right? So you're going to have to parse. In other words, you're going to have to take apart and analyze all of the detritus, all of the junk that's in the word problem, and pick out the data that you really need. So I'm going to describe a problem. I'm going to say that we're going to do a study and we're going to sample doctors and lawyers, random sample, right? Random and independent. In other words, not the same family or anything like that, not for the same locality. We're going to randomly sample New York State, through all parts of New York State, randomly sample New York State doctors and lawyers who have been in practice for 10 or more years. Okay, all that really doesn't mean anything to us aside from it describes what this study is. But we're going to get to the information that we really want, right? So the variables we have here is one is a categorical variable. Are we talking about a doctor or are we talking about a lawyer, right? So we have a categorical variable, occupation, and our numerical variable is their salary. Okay, we're going to ask them what they made, let's call it income instead of salary. You know, nowadays doctors and lawyers, they got all kinds of side deals going on, especially doctors own MRI facilities and who knows what they do, right? So at any rate, I won't go into that. So at any rate, let's say we sample these doctors and lawyers, and let's say we sample our sample size. Maybe it's not even this time. Why would it always be even? I'm going to say our sample size is 40 doctors and 60 lawyers we got to respond to our survey, right? And it turns out that the mean income for doctors is $200,000, and the mean income for lawyers is, let's say, $180,000. Okay, and the standard deviation for doctors was $20,000. And the standard deviation for lawyers was, let's say $18,000. Okay, well, I'm going to examine this. What I really want to know is, do all of the doctors, does the mean for all of the doctors in New York State, is that different than the mean for lawyers in New York State, all of the lawyers in New York State? In other words, mu for the doctors or mu for the lawyers. Are they the same or are they different? So I need to set up a hypothesis. Okay, so the first thing I need to do, number one, is I have to determine what my sample sizes are. First of all, before we do anything else, we want to set up our H null, our null hypothesis, and our alternative hypothesis. Okay, I'm going to do that right now. So mu is equal to, my mean for mu for doctors is equal to mu for lawyers. My null hypothesis is that there's no difference. H null. There's no difference in the salaries. Not X bar. Notice I didn't write X bar. I'm really interested in the mean for all doctors. Okay, so our alternative hypothesis is that the mean income for doctors does not equal the mean income for lawyers. Now, just because our sample was 180, remember I set up my null hypothesis, or I conceived this study before I actually collected the data. So I'm not going to prejudge whether or not lawyers make more or doctors make more, although now that I've collected the data, it looks like it might be going one direction. But is this this is a pretty big standard deviation, pretty big variability that we have here in each one of these cases. Is the difference between the mean that we had for doctors that we collected and lawyers, is that big enough difference for us to reject the null hypothesis and with less than 5% chance of being wrong? So we want to set up our null and alternative hypothesis. Second thing is, we want to know what is our level of confidence that we want here. How much error, what level of error are we willing to accept? So like our confidence interval, we got to decide that ahead of time. In this case, I'm going to say alpha, the probability that we would be wrong. We don't want it to be any bigger than 5%. Okay, that's kind of correlates to a 95% certainty. 5% chance of being wrong means kind of you're 95% certain that you're right, right? So at any rate, alpha is equal to 0.05. So we want to be able to demonstrate with less than that probability that we would be not be wrong if we reject the null hypothesis. So our job here now is to decide whether we can reject the null hypothesis. Do we have the evidence that we need to reject the null hypothesis? Okay, so now the way we're going to do this is we want to know if these two means are far enough apart from one another that I could say with 95% certainty that they didn't come from the same population, that there really is a different salary level between these two groups. Okay, and how do I do that? Well, I do that by calculating either a t-score or a z-score. Okay, so now I don't know, when I take samples, I don't know the population standard deviation. But like before, my sample size is important here, right? So I might use Z or T. I'm never wrong using T if I don't know the population standard deviation. If I did know the population standard deviation, if it was given to me that let's assume that it's this much, I would use Z. I would be looking for a Z score. Let's say I'm looking for a T score, right? So I'm looking for a T value now. How big is the T value based on the difference of these two means? And what is the T-score equal to? It's equal to the number of standard errors apart that this mean is from this mean. So how would I calculate that? We're going to use a formula that we've learned before. T is equal to X bar for the doctors minus X bar for the lawyers over the standard error. In other words, it's just the number of standard errors apart. If the standard error turns out to be 10,000 and the difference turns out to be 20,000, then that's two standard errors, two 10,000s apart. So T would be equal to 2. Now the question is that a big enough T value? In other words, is that far enough apart? If it were 30, if this were 200,000, this was 170,000, and this was 10,000 standard error, then that would be 30,000 over 10,000. That would be 3 standard errors apart, further apart. More evidence that they're different and that I can reject the null hypothesis, again, depending on if my t-score is big enough for that sample size. Okay, so I'm going to look at my sample size. And when I look at my sample size, I'm going to determine what my degrees of freedom is going to be. So if my standard deviation, two standard deviations for two samples are close, are similar, I can just determine that the degrees of freedom is equal to sample size 1 plus sample size 2 minus 2. Okay, or in this case, it's going to be equal to 100 minus 2. It's going to be 98 in this case. That's our degrees of freedom. Okay, so now at this point, I'm going to say, okay, let's pick out a critical value for T. Okay, well, now I know what my degrees of freedom are, and I know what my alpha is. I can go to my table, and I can figure out what's my critical value of T. Well, let's see, 98, I'm going to use 100 because it seems like it's close enough. So 5% 5% chance of error is going to be a 95% confidence interval, but it's going to be 95% certain. And notice it says right tail, but there's going to be 2.5% in either tail, left tail and right tail. And since we're sticking with two-tailed hypotheses, we're going to double that, so it's 5%. 95% confidence represents the same thing as 5% chance of being wrong if you reject the null hypothesis. So I'm going to use our critical value of T is going to be 1.9. I'm going to call it 1.98. Okay, actually, tell you the truth, 1.9. Where did I put it? 90. So 100 would be not 1.98. Yeah, let's call it 1.98. It's close enough. Okay, so our critical value of T critical equals 1.98. In other words, the T value we calculate has to be bigger then this value, the two means have to be further apart than this t critical in order for me to have less than 5% chance of being wrong. Okay, so I need the t that I calculate to exceed that number. If we're a smaller sample size, that number would be a bigger number that we would get from the table. Okay, so let's calculate this. This is equal to 200,000 minus 180,000 is 20,000 over the standard error. Now, how do I calculate my standard error? Now, this is the toughest kind of, this is of these problems, this is going to be the toughest that I might ask you to do on a test. And in fact, I might not ask you to do this necessarily on test. I might ask you to do something similar, which I'll show you in a few moments, or I might leave it up to let you use SPSS to calculate this. Okay, so now we have a document that we had in class. We have a document that we had in class, which was variations, t-test variations, I think I called it. Let me see if I can't find it. T-test variations, there it is. Okay, good. Okay, if I go to this document, it'll show me if the two populations have similar or equal standard deviations, if the two samples have similar or equal standard deviations, and I defined that as one is not double the other. So if you look at this, one is 10,000, the other is 18,000. So one's not double the other. So I'm going to say that they're close to one another. Okay, in order to calculate the standard error, now look at this formula here. It's kind of a little hidden here, but what is this? T is equal to x bar 1 minus x bar 2 divided by something. It's divided by the pooled standard deviation. In other words, since these sample sizes are different, one group's going to influence the standard deviation more than the other if I want to put them together, since they're pretty close. And I have an advantage there. Notice this part we already did, degrees of freedom, n1 plus n2 minus 2. So this part down here, it's not stated that way, but you can see x bar 1 minus x bar 2 divided by something to get the t-score. That's got to be the standard error. That is the standard error down there. So how do I calculate that? Well, you got to do it in two steps. The first thing you got to do is calculate the pooled standard deviation. And what is that equal to? Let me see if I can't do this without messing stuff up here. Oops. Okay, I need to move stuff around here so I can see it. Okay, so pooled standard deviation. It's tedious, but it's tedious, but it's not a hard calculation, just tedious. The pooled standard deviation is equal to the square root of the sample size of the first group minus 1. Well, what is that? That's 39, right? The lawyers were 40. 39 times the standard deviation squared, which is 18,000, which is 20,000 squared, plus sample size 2, which is 60 minus 1 is 59, times 18,000 squared over n2 plus n1, n1 plus n2 minus 2, which is 98. So I got to figure out all this stuff and all this detritus in the middle here to calculate this, right? So I'm going to do it. Normally I would use Excel for this, but I just want to go through the calculations with you in case you feel uncomfortable using Excel. I want to make sure you can still do it. Okay, so first thing I'm going to do is 20,000 times 20,000 times 20,000 is equal to, whatever that comes out to. I'm a little sorry I count 400 million. A little sorry I use such large numbers at this stage. Times 39 equals this ridiculous number now, right? So I'm going to put that into memory. I'm going to either write that down or put it into memory. I'm going to put it into memory. Now I'm going to clear the display, and I'm going to do the other part. 59. Whoops, let me clear that. First, I want to do my multiplication. I can do it either way, it doesn't matter. 18,000 times 18,000 times 59 is equal to this ridiculous number, and I'm going to add that to my memory also, plus. So now in memory, I've got this number plus this number. And I'm going to recall that. So there's the total of those top part, and I'm going to divide it by 98. Okay, that's the number I wind up with is 354 million, it looks like. Now I'm going to take the square root of this, right? Because I'm going to take the square root of the whole thing. That gives us our pooled standard deviation. And I bet you that it's going to be somewhere around 19,000, right? Because what do I have here? One standard deviation is 20,000. One is 18,000. It's going to be around 19,000. And you know the sample size of this group is bigger. So I'll bet you it's going to be closer to 18,000. So a little under 19,000. Let's see how good my guess is. Square root. And look, it's 18,821. What a surprise, right? Okay, but we did that calculation because that gave us our pooled standard deviation. Now I'm going to clear memory here, and I'm going to put this number into memory. Okay, so 18,821. So our pooled standard deviation is equal to $18,821, right? So now, in order to calculate our standard error is the bottom of that equation. It's equal to the pooled standard deviation times the square root of 1 over n1 plus 1 over n2. Okay, so what is that? That's 18,821, right, times the square root of 1/40th plus 1/60th. Okay, so that's going to get a little complicated now. Let's go back here. Okay, actually, I need to get square root of that, right? I didn't put that on there. I'll put it on there when I get back. Oh, I did put the square root of. Okay, so this is what's in memory is 18 or whatever. I'm going to clear that. It's still in memory. So I need 1/40th, 1 divided by 40 is equal to 0.025 plus I need to add to it 1/60th. So remember that 0.025. 1 divided by 60 is equal to that plus 0.025. Okay, so that is the sum of what's inside that square root sign. So now I'm going to find the square root of it. And it comes out to that. And now that whole thing, I'm going to multiply by 18,800. So I'm going to say times, recall memory, and get equals. And it comes out to be 3,841. That's our standard error. 3,842. Okay, so 3,842. 842, okay, is equal to our standard error. So that's what goes on the bottom of this equation, 3842. Now you will notice that it's a little funky down here, right? Because it doesn't just say, here's my nice simple formula here, but the complication here was this bottom part. We had to go through this calculation. I promise you, this is the toughest that you would have to do for this kind of problem. Okay, so now, at this stage now, I have to look at my critical value at t, 5, calculate my, first of all, number 5, do we assume equal variance? Okay, I will not give you on the test a situation where you don't assume equal variance because things, well, I don't think I will. I will show you the difference now, but I might try and avoid that. Actually, sometimes it's a little bit simpler, but I'll show you in a second how that would be done. So 5, do we assume? If we assume yes, okay, and let me find that Word document. If we assume the variances are equal, and again, one is not double the other. Oops, that's not what I wanted to do. Let me keep it from opening that. Yes. Okay, what I wanted to do is get back to that Word document. T-test variations. Here we go. Okay, If they're unequal, if one's more than double the other, you would use a different set of formulas when these standard deviations are not assumed to be equal. Again, it's x bar 1 minus x bar 2 over the standard error, except this time you don't have to go through two steps if you assume that they're different. If one's more than double the other, you only have to go through this one step using the standard deviation of first group and the standard deviation second group and sample sizes. That the degrees of freedom is a complicated calculation. Most of the time, to avoid that for convenience, we just say take the smaller of the two sample sizes and subtract 1. And we would use that as the degrees of freedom. Okay, so in the case we have here, it would have been 40 minus 1, or 39 degrees of freedom. So it would be a pretty conservative way of handling this. Okay, so let me go back here and let's finish this up. So now our t-score that we calculated, how many standard deviations apart, standard errors apart, are these two means? Well, 20,000 over 3,800, 42. Well, what does that come out to be? You can see already it's going to be a very large number, right? Okay, so clear, 20,000 divided by 3842. I don't know if I have it in memory or not. I'll just do it this way. Comes out to be 5.2 is our t-score, our calculated t-value, and so on, right? So is our calculated t-value greater than our critical value of t, right? So if it is, okay, so we calculate our, number 6, we calculate our standard error, right? And 7, we calculate our t-score. And 8, we compare it to t-critical. So our t-score comes out to be 5.4. T-critical is 1.98. So these means are so far apart that it's unlikely that these two samples represent the same salaries, the same population. So because T that we calculated is greater than T-critical, with less than 5% chance of being wrong, I can reject my null hypothesis and accept our alternative hypothesis. Okay, if T critical had come out to be 1.4, well, it would have been less than, if T had come out to be 1.4, then it would have been less than T critical. So I failed to reject my null hypothesis. That doesn't mean your null hypothesis is true. You might have been very close to rejecting it, but just not have quite a big enough sample size or have quite enough evidence. So you don't say anything about whether you believe it or not. You just say you failed to reject your null hypothesis. Okay, so I just want to, one other situation here I want to go over, and that is, what if you only have we have something that you might get on the test that's a lot simpler, is a single sample t-test. Okay, how does that work? Okay, well, that's a situation where, let's say that the American Bar Association, they've been in the news lately in New York State, right? The American Bar Association, they've been in the news because they've been critical of some of the judicial nominees lately. So we've been hearing quite a bit about them. Let's say the American Bar Association did a survey of all the lawyers in New York State, and they found that the average mu for lawyers, we know what the mu for lawyers is, turns out to be let's say we keep it 180,000. Right? Turns out that that's the actual salary. Now, let's say that the AMA, well, they don't, they're a little bit more private. Maybe they didn't do anything like that, but they let us survey, let's say they let us survey their members. So we survey 100 of their members, randomly chosen members, and we find that the average salary of their members is $190,000, and the standard deviation for those 100 members is equal to $10,000. Okay, well, let's say based on this, we want to know the same thing we knew before. In other words, H null is the mean for doctors is equal to the mean salary for mean income for lawyers, or our alternative that they're not equal. And H alt, right? Okay, so how do I do this now? Well, I'm still going to do a t-test. So t is going to be equal to, well, in this case, x bar is my sample mean for the doctors. I don't know the mean for the doctors. I only know the sample mean. But I do know the mean for the lawyers is 180,000. So it's x bar minus mu, the difference between my estimated mean for doctors and my known mean for lawyers, over the standard error. Well, it's going to turn out to be a lot simpler now, because my sample size is 100. My degrees of freedom is equal to 199, is equal to 99, right? Because I only have one sample here, right? I'm not going to subtract 2, just 1. And I already know that that tells me that T critical, and I'm not going to bother to look it up because we've looked it up already, right? 1.98, right? That's what it was for 100 when we looked it up before. So T critical is 1.98. So I need my difference between these two means to exceed 1.98 before I can reject my null hypothesis. Okay, so I need to calculate my standard error now. Well, you want to know something? This is just a simple sample here. So I calculate my standard error the same way I do it for my confidence interval. My standard error is equal to sigma over the square root of n, right? Because that's all I know. I don't have to pool standard deviations. I don't have to decide whether they're equal or unequal. I just only have one sample. So since I don't know the standard deviation of population, I'm using S over the square root of n, right? So this is going to be equal to, well, what is this? What is the standard deviation? It's 10,000 over the square root of the sample size, which was 100, which is 10. So my standard error is 1,000. Okay, so T is the difference between these two, which is 100 and which is 180, which is minus 10,000, over my standard error, which is 1,000. So my t-score in this case is minus 10. Doesn't matter, sign doesn't matter, right? Is minus 10. So again, I'm in a situation where my calculated t-score is so large that I can reject my null hypothesis. Okay, had the difference in salaries been, say, let's say it had been one x bar came out to be let's say x bar for the MA had come out to be 180, let's see, 185, let's say. Let's see, 190. Let me think for a second here. 181,000. Then the difference would have been 1,000, right? Let's say 181,500. Difference would have been 1,500, right? Over 1,000, right? This 180,000 minus 181,500, and our t-score would have been minus 1.5, and a t-score of minus 1.5 doesn't exceed our critical value of t, so I can't be 95% certain that I can reject my null hypothesis. In other words, there's more than a 5% chance I would be wrong if I reject my null hypothesis. So in that case, I would fail to reject my null hypothesis. Okay, so I'm going to call it a day for now. I am going to record some of these problems solved with SPSS. So when you take and I'll post those tomorrow. So that if you wind up using SPSS, if you wind up having to use SPSS or prefer to use SPSS, I'll probably provide the data set for you, so you can go ahead and do that instead. Okay, so for alpha is equal to 0.05, if critical is less than alpha, if T critical is less than, T critical has to be, T critical, you compare T critical to the T value, right? That lets you know whether or not your probability of being wrong is greater than or less than 5%. So you reject the null hypothesis is if you reject the null hypothesis if T that you calculate is bigger than T critical.